The complexity of the universe. We keep wondering why we exist, why there are planets and stars, and what other possible destinies might have been had the universe evolved differently. Often we don't pay attention to problems until they become critical, even if they will eventually affect us. One such concern that has recently drawn the eyes of astronomers and scientists around the world is the strange and unsettling behavior of Betelgeuse, also known in some colloquial or popular forms as Betelgeuse or Betelgeuse, one of the largest stars in the firmament. This colossal star has begun to show signs of instability, trembling alarmingly, which could indicate that something frightening is happening within its massive structure. Betelgeuse has long been the subject of study because of its gigantic size. In fact, it is so huge that it makes our Sun seem tiny in comparison. It is not a star like other stars and never has been. Betelgeuse is a red supergiant, a classification that puts it among the largest types of stars known to science. And despite its prominent appearance in the night sky, Betelgeuse is actually much more distant than it appears from Earth, roughly 600 to 700 light-years away, depending on the measurement used. Although this distance may not seem significant at first glance, in cosmic terms, it is immense. Even if we could travel at the speed of light, which is far beyond our current capabilities, it would take many centuries to reach it. Something impossible with current technology. Under normal conditions, the light journey times and scale give us a humbling idea of the magnitude and strength of the star, which has been shaking intensely for some time now, captivating astronomers across the globe. Stars, although they appear quiet and motionless from our perspective here on Earth, are in fact not quiet at all. Regardless of their size, they are dynamic, turbulent, and full of activity. Scientists do not yet fully understand all the signals that Betelgeuse emits. It has been labeled a semi-regular variable red supergiant. Its brightness varies in cycles with periods ranging from a few hundred days to several years. These gradual changes show us how dynamic this star is. Another interesting thing about Betelgeuse is that its brightness varies considerably, ranging from magnitude about plus 0.0 to plus 1.6, visual magnitude, depending on whether it is expanding or contracting or whether dust or other factors obscure or dim its light. These variations in brightness occur in cycles. The primary pulsation cycle has been observed at about 400,425 days, and a longer cycle of several years has also been noted. Occasionally, these cycles overlap in ways that lead to unusually dim or bright phases, which capture the attention of astronomers who closely monitor such fluctuations. For example, during the so-called Great Dimming in 2019 to 2020, Betelgeuse dropped to among its faintest brightnesses in over a century of observations. Not only is its brightness remarkable, but also its intense red color, which is due to its surface temperature of about 3,200–3,700 Kelvin, much lower than the Sun's (500–6,000 Kelvin. Because of its lower temperature, Betelgeuse emits less energy per unit surface area, making it appear less luminous in visible light despite being one of the largest known stars in radius. For all its massive size, Betelgeuse has been relatively stable until these recent oddities. Despite being a pulsating giant, it has shifted from calm regularity to more volatile behavior, which is, to put it mildly, alarming. This growing instability is a sign of a major transformation occurring inside Betelgeuse. Astronomers believe that the star's gas shell is changing. The core has long been burning hydrogen but is running out of it, and fusion processes have evolved. Helium and heavier elements now play an increasingly larger role in its internal fusion processes. When hydrogen fusion in the core slows down, outer layers expand, causing the star to swell even further. During this phase, helium accumulates around the core, which becomes hydrogen depleted, and a new fusion process begins. This process, often called helium shell burning or envelope burning, involves the fusion of helium into heavier elements such as carbon and oxygen. These reactions release energy that counters gravitational collapse of the outer shells, but helium burning is not as steady or constant as hydrogen burning. This irregularity leads to accumulations of energy and sometimes bursts or large ejections of mass. These bursts destabilize the star's structure, causing its outer layers to expand and contract, which we perceive as pulsations that alter Betelgeuse's brightness over time. Such pulsations release enormous amounts of energy and generate strong stellar winds. These winds are so intense that Betelgeuse loses mass loss that not only removes outer layers but also alters the internal distribution of matter and energy, further influencing the star's evolution. As the outer layers expand and contract, a constant pulse is generated. We perceive this rhythmic activity as changes in its brightness, similar to the beating of a heart. To better understand these phenomena, astronomers employ a variety of methods. Among the most important are photometry and spectroscopy. Photometry measures the amount of light emitted by the star at different times, allowing us to observe changes in its brightness. As with Betelgeuse's pulsations, this gives valuable clues about what is happening inside. Spectroscopy analyzes the star's light at different wavelengths, revealing details about its temperature, motion, radial velocity, and the internal processes that generate its signals. When Betelgeuse pulsates, its spectral lines shift, redshift or blueshift, due to expansion and contraction, letting scientists deduce what is going on in deep layers. Together, photometry and spectroscopy allow scientists to build a more complete picture of Betelgeuse's internal structure and track its evolution over time. Astrophysicists also use powerful computer models and simulations to piece together how stars like Betelgeuse behave. From the fundamental equations of stellar structure to complex fluid dynamics, convection, mass loss, radiation pressure, and fusion, the models try to simulate how Betelgeuse will behave as its eye. Internal conditions change. Convection is particularly important. In this process, energy generated in the core is transported toward the surface via giant currents of hot plasma rising and cooler material descending. These convection cells can be enormous, covering a significant fraction of the star's surface, and their behavior can cause surface temperature variations and spots of cooler or hotter plasma, which affect brightness. These changes in energy transport caused by convection currents are responsible for the variations in brightness we observe. The cycles of brightness are linked to the rhythmic expansion and contraction of the outer layers. When the star expands, its surface cools and dims. During contraction it heats up and brightens. This process is the result of complex interactions between two fundamental forces, gravity pulling inward and radiation pressure pushing outward. These opposing forces create a delicate balance, leading to the star's periodic expansion and contraction over time. What is especially fascinating is that Betelgeuse has recently exhibited phenomena that fall outside of its previous patterns. In late 2019, observations showed that Betelgeuse underwent a dramatic and historic dimming now known as the Great Dimming. During this period, astronomers detected what appears to be a surface mass ejection, SME, a massive expulsion of surface material which then cooled and formed a dust cloud that partially blocked light from the star as seen from Earth.